welcome to the Deep Dive. Today, we're going straight into the language spoken inside your computer at its highest speeds.
PCI Express Transaction Layer Packet.
Right, TLPs. PCIe is, well, it's the fundamental way all those super fast components talk to each other.
Absolutely. And the real workhorses in that communication.
These TLPs. They're the absolute basic units of data being moved around.
Think of it like this. If your computer is a bustling city, PCIe is the network of, high-speed roads connecting everything.
Okay.
And TLPs, they're the delivery trucks, basically, constantly carrying information back and forth. The sources we've looked at really let us peek inside these trucks.
See how they're packed, labeled, and sent off.
Exactly.
So our goal today is really to break down this crucial aspect of your computer's inner workings. We want to understand what these TLPs are all about.
And the critical role they play in keeping everything running smoothly and, quickly.
That's like understand the grammar of your computer's most vital conversations. Okay, let's unpack this.
Right. So our exploration into the TLP, it really begins at the transaction layer.
Okay.
In the PCIe protocol stack, this layer acts as the go-between. It sits between the device's core logic.
The part that actually wants to send or receive the data.
Yeah, exactly. And the data link layer, which handles the more, let's say, nuts and bolts aspects of making sure the connection itself is reliable.
So the transaction layer is like the dispatcher then. It takes the high-level requests from a component and figures out how to break them down and package them into these TLPs for their journey across the PCIe connection.
That's a great analogy. And when TLPs arrive, it's also the transaction layer's job to process them and hand the useful information, up to the device core.
Makes sense.
And this dispatcher, it manages traffic across 4 main zones within the PCIe system. We call them address spaces.
Right. Memory, I/O, what else?
Memory space, that's for moving data to and from your main RAM. Then I/O space, which lets the CPU talk to peripherals using specific port addresses, like sending mail to a specific office, almost. Configuration space is crucial for boot up, discovering devices, setting them up.
Gotcha. And the last one?
Message space. This is for quick signals, think digital sticky notes, things like interrupts or power management events, without needing dedicated memory or I/O addresses.
Okay, so a TLP gets on the PCIe highway, carrying specific info for one of these 4 zones. Now, what does one of these packets actually look like? What's inside the truck?
Well, at its core, every single TLP has a mandatory header.
Always there. The address label.
Exactly. And then an optional data payload.
The actual cargo.
Right. Whether it's there and how big it is really depends on the transaction type. A write operation sending data.
It definitely needs a payload.
Right. But if you're just asking to read data, the initial TLP often won't have one. It's just the request itself.
Yeah, that makes sense. You wouldn't send an empty box to ask for something. But you mentioned sometimes these TLPs have other optional bits attached.
Yes, sometimes. Occasionally, a TLP might have prefixes added before the main header.
Like extra handling instructions.
Sort of. Special notes attached to the outside. And then at the very end, possibly after the data payload, you might find a TLP digest.
Okay, what's that?
It's an optional end-to-end cyclic redundancy check, ECRC. Think of it like a tamper-proof seal.
A digital fingerprint.
Exactly. To make absolutely sure the data arrives exactly as it was sent across the whole journey.
So adding that extra layer of security guarantees integrity.
Okay, so the transaction layer builds this TLP header, maybe data, maybe a digest. But it doesn't just magically appear on the connection. Other layers are involved.
Oh, absolutely. Once the transaction layer assembles its TLP, it passes it down to the data link layer.
Right.
This layer adds its own info. For reliability of the direct connection between 2 components, it adds a sequence number at the beginning.
To keep track of the order, like numbering trucks in a convoy.
Precisely. And it also sticks a link CRC or LCRC at the end. This is a local error check, just for that specific point-to-point link.
So if something goes wrong just on that hop, the data link layer handles it, automatically retransmits that TLP if the LCRC check fails.
So LCRC is like a quality check at each handoff point.
Okay.
And then it moves down again.
Yeah.
To the physical layer.
Exactly. The physical layer takes the whole package transaction layer stuff, data link layer additions, and handles the actual physical signaling.
Getting it onto the wires.
Right. Adding start and end markers framing, encoding the data into a suitable format like 8B10B or the newer 128B, 130B, and finally serializing it, turning it into that stream of bits sent across the physical PCIe wires 1 bit at a time.
Well, it really is a team effort.
Yeah.
Each layer has its critical job. Transaction layer for the info itself.
Data link for reliability across each segment.
And physical for actually sending and receiving. And you mentioned different error checks happening.
Yes, different scopes. The LCRC is all about that immediate connection, point to point. If a packet gets corrupted right there, the data link layer tries again. But the optional ECRC, that provides end-to-end protection. It verifies integrity all the way from the original source to the final destination, managed by the transaction layer.
Got it. And all these sizes, structures, measured in double words, DW.
That's the unit, yes. 32-bit chunks. So a 3DW header is 3 times 32 bits, 96 bits, or 12 bytes long.
Right. Okay. Now let's really get into the heart of it. That standard TLP header, the mandatory starting point.
That's right. Whether it's 3 or 4 DWs long, it's absolutely packed with essential info. It tells the receiver and any switches along the way exactly what kind of transaction it is, where it's going, how to handle it.
Like the TLP's passport and detailed itinerary.
Perfect analogy.
And the size, 3DW or 4DW, that's determined right at the start by the format and type fields in the first of double word.
Correct. And also by the needs of the transaction. Like if it needs a full 64-bit memory address, that pushes it to 4DW.
Makes sense.
And the organization is quite clever, especially for a serial link like PCIe. Those FMT and type fields, crucial routing info like address or ID, it's all right there in DW0, the first double word.
So switches can make forwarding decisions really quickly without waiting for the whole header.
Exactly. Minimizes delays. It's like putting the most important delivery info right on the very front of the package. Fast sorting.
Smart. And within each 32-bit DW, the bytes are big endian.
Correct. Within each 4-byte chunk, the most significant byte goes first. Standardized ordering avoids mix-ups.
Okay. Let's break down those DWs, starting with DW0, the universal ID tag, you called it.
Yeah, pretty much. First up, the format field, FMT, tells us 3DW or 4DW header, and crucially, is there a payload?
Right. And that weird value, 100B, not a standard header.
No, that's the flag for a TLP prefix, something we'll get back to.
Okay.
Right next to it, the type field works with FMT to define the exact TLP type. Memory read, memory write, IO config, completion, message. This field nails it down.
And for messages, the lower bits are for routing.
Yes, for message TLPs, the lower 3 bits of type act as a routing subfield. That's flexibility there.
Okay, moving along in DW0. Byte 1, traffic class TC, quality of service.
Yep, assigning priority. Mapping TLPs to virtual channels dedicated lanes on the highway ensures important stuff doesn't get stuck.
And messages usually use the default, TC0.
Typically, yes. Then in that same byte, there's an attribute bit for ID-based ordering, IDO. Came in PCIe 2.1, helps maintain order for TLPs from the same requester. Then the LN bit, lightweight notification. PCIe 3.0 feature, we'll discuss that one later.
Okay.
And right next to that, the TH bit, TLP hints. PCIe 2.1, again, often involves steering tags, another advanced topic for later. So yeah, even just byte 1 of DW0 is dense.
No kidding. Okay, byte 2 of DW0, TD bit, TLP digest.
Right. If TD is 1, it means that optional 32-bit ECRC digest is tacked onto the end of the TLP for that end-to-end check.
Got it. And EP, poison packet, sounds bad.
It does. If EP is set, it's a warning flag. Means the data payload might be corrupted, carries error info along with potentially bad data.
Alerts the final receiver. Okay, then ETRI again, but for general attributes, RO and NS.
Yes. RO is relaxed ordering, allows this TLP to potentially bypass earlier ones, can boost performance sometimes. NS is no snoop, a hint for memory requests.
Tells the completer it doesn't need to check caches for consistency.
Right. The requester already knows the state. Saves time.
And finally, rounding out DW0 and into DW1, the length field. 10 bits for payload size in DWs.
Correct. Payload size in double words. If no payload, it's reserved. And there's a limit. The max payload size register sets the cap for each device.
As 0 means 1024 DWs, the max.
Yep, that's the encoding for the maximum size. Quite a bit packed into DW0.
Definitely. Okay, DW1, more specific details. Requester ID first.
Yes, 16 bits. Uniquely identifies who sent the TLP, bus, device, function number, crucial for non-posted requests like reads.
So the completion knows where to go back to.
Exactly. And ARI, alternate routing ID interpretation, might change how this is read slightly, allowing more functions per device.
Okay. Then the tag field, 8 bits, transaction number.
Pretty much. For non-posted requests, like a tracking number, the completer sends the same tag back in the completion.
So the requester can match request and response.
Right. Ignored for posted stuff like memory writes, as they don't get a completion back. And remember, later PCIe introduced longer tags. We'll get to that. Default might only use 5 bits, unless extended tags are enabled.
Good point. After the tag, byte enables. First DWBE and last DWBE.
Yes, 4-bit masks each. Tells the receiver which specific bytes in the first DW of the payload and the last DW of the payload are valid.
So you can write just 1 byte, for instance.
Exactly. Precise control. And for zero-length reads-writes, used for flushing, the first DWBE must be all zeros.
Interesting. Okay, that covers DW0 and DW1. Now, DW2 and DW3. These change meaning based on the TLP type?
They really do. For memory or I/O requests, DW2 and DW3 for 64-bit holds the target address, memory address or I/O port.
32-bit uses just DW2, 64-bit uses DW2 for lower, and DW3 for upper.
Correct. And remember, addresses are DW aligned. Lower 2 bits are always 0, not transmitted.
Got it. What about for completions, the responses?
For completions, DW2 and parts of DW1 carry completion info. You get the completer ID who is sending this back, completion status successful, error, unsupported request, completer abort.
The outcome.
Right. Then BCM, byte count modified, usually 0 now, more for older bridges. Then the byte count, how many bytes are remaining for the whole original transaction, including data in this completion.
Okay.
And lower adjust the byte offset of the first data byte in this specific completion. Important if a big read comes back in pieces.
Wow, lots of detail to track there.
Yeah.
And for message TLPs, how do they use DW2 and DW3?
Well, the actual message code is in DW1, byte 7. Defines the specific message like interrupt or power event.
Right.
If the message uses odd-address-based routing indicated by the type field's routing bits, then DW2 and DW3 will hold the destination address.
But if it uses ID routing or broadcast?
Then DW2 and DW3 might just be unused, reserved.
So it really all hinges on decoding FMT and type in DW0 first. That dictates how you interpret everything else.
Absolutely. That's the starting point for any TLP processing logic. Our sources had a great table summarizing common FMD type combinations.
Yeah, showing memory read-write, I/O, config, messages, completions, and importantly, how each is routed, address, ID, or message type.
It really highlights that balance the header is compact, 12 or 16 bytes, but carries so much rich info, fast routing, and support for advanced features.
Pretty impressive. Okay, and that leads us nicely into extending that information. TLP prefixes.
Oh, yes, the optional add-ons.
Single DW structures attached before the standard header. Little preambles.
That's the idea. Their purpose is to carry extra info that just doesn't fit in the standard header. Allows flexibility, new features, vendor stuff, without redesigning the core header.
Optional add-on modules for the data truck.
Exactly.
And the telltale sign is that FMT field in the prefix's first byte being 100B.
Right. And you can have multiple prefixes, one after another. Each prefix starts with FMT 100B. The system knows the real header starts when it sees a different FMT value.
Okay. And like the header, the first byte of a prefix has FMT 100B and a type field. And that type determines what the rest of the prefix means.
Correct. Now, there's a key distinction based on that prefix type field, local versus end-to-end.
Right. Depends on the last bit of the type field.
Precisely. If the least significant bit is 0, it's a local prefix, LPRFX, info relevant only to the immediate link.
So a switch might look at it, use it, maybe even change or remove it?
Exactly. Its scope is just that segment. The format is FMT 100B, type ends in 0, like 0LLLB. Vendor-specific 1 is an example.
Okay, like a note just for the next stop. But if that last bit is 1...
then it's an end-to-end prefix, EPRX, FMT 100B. Type ends in 1, like 1EEE. This info needs to persist all the way from originator to final destination.
Needs to go through switches untouched.
Right. Used for features needing context across the whole path. Vendor-specific 13 is an example. Endpoints need to support these if relevant features are enabled. Switches are expected to forward them, but might have limits or filters.
So switches need to know. Process locally, LPRFX, or pass through, EPRFX. That last bit is key.
Absolutely. There was a table summarizing these categories, too.
Now, connecting this to PCIe 6.0, orthogonal header content, OHC, sounds like prefixes are evolving.
They are. PCIe 6.0 SWIT mode uses OHC for optional info in a more structured way. OHCD specifically replaces many end-to-end prefix functions.
So less reliance on prefixes for extended data in FLIT mode, moving towards a more integrated approach.
Seems to be the trend, yes. Prefixes were flexible, indicated by FMT 100B, local, or end-to-end. Important historically, but OHC is taking over in the newer high-speed mode.
Okay, good overview of prefixes. Now let's dig into some of those advanced features flagged in the header. Lightweight notification, LN. Sounds like cache coherency assistance.
That's exactly what it is. Optional feature from PCIe 3.0 via an ECN. hardware-assisted cache coherency between the host memory CPU and I/O devices.
So an I/O device can say, tell me if this specific cache line in host memory changes.
Basically, yes. It allows endpoints to register interest. If the host modifies that line, it sends a notification directly to the interested endpoint.
A lower latency way than the device constantly checking or relying purely on software.
That's the goal. Lower latency, more efficient than polling or just flushing caches all the time. It supports unicast or even multicast notifications.
And we saw the LN bit in DW0 of the header indicates this.
Yes, bit 1 in byte 1 of DW0 in a memory request TLP. If set, it's an LN read or LN write interacting with the host's LN tracking.
And the actual notification comes later.
Yes, when the host updates the cache line, it sends a separate message TLP and LN notification message to the endpoint.
Sounds like it needs support everywhere, though. Host CPU, root complex, memory system, firmware defining LN ranges. The endpoint device needs logic for it, and the drivers need to manage it.
It's a full system-level feature, absolutely.
Yeah.
Requires coordination. But interestingly, some newer tech, like Intel TDX, actually recommends against using LN. And maybe more significantly, the LN bit itself is deprecated in PCIe 6.0's flip mode.
Really? So maybe it didn't get wide adoption, or alternatives emerged.
That seems likely. While the idea was sound, perhaps practical limitations or other coherency methods, software CXL became preferred. Limited use seems to be fading out.
So LN, optional PCIe 3.0 feature for I/O cache coherency via notifications. Required system support, but limited uptake and now deprecated in some areas in future specs.
Yeah.
Okay. Next up, TLP processing hints, DPH, and steering tags, ST, performance optimization.
You got it. Another optional feature, via ECNs after PCIe 2.0, aimed at boosting I/O performance, especially in complex systems like NUMA.
Non-uniform memory access, where accessing different memory banks takes different amounts of time.
Right. TPH lets the requester, usually an I/O device doing DMA, include hints in its memory request TLPs.
Hints for the root complex or memory controller, like handle this data this way for best results.
Exactly. Guiding the system for better decisions. Potential benefits. Lower latency, reduced coherency overhead, maybe lower power.
How so?
Well, a key use is intelligent cache injection. The endpoint writing via DMA can hint, put this data directly into CPU Core X's cache.
If that core is likely to need it soon, skips writing to main RAM first.
Right. Big latency saver. Also helps differentiate cacheable data from bulk transfers that might just pollute the cache.
And the TH bit in DW0 indicates TPH info is present.
Yes. TH is bit 0 in byte 1 of DW0. That flags the presence of TPH info. This info usually includes processing hints, PH.
Qualitative info, like how the data will be used.
Yeah, typically 3 bits or so, frequently read, written, high temporal locality, the encoding can vary. And then there's the optional steering tag, ST.
More specific, system-dependent identifier.
Right. Often 8 bits, maybe more. The meaning isn't standard PCIe, it's platform-specific. The root complex uses it to steer the transaction.
To a specific CPU core's cache or specific NUMA node.
Exactly, those kinds of things. Direct placement guidance.
But how does the endpoint know which ST value to use?
That requires system coordination. TPH is an optional capability. Both endpoint and RC must support it. Then it needs enabling, usually by the driver.
Okay.
The driver queries the system firmware, like ACPI, to get the correct ST value for the desired target, e.g. CPU Core 3's cache.
So the firmware knows the system's internal map.
Right. Driver gets the ST, programs it into a steering tag table in the endpoint device via MSIX or a TPH capability structure.
Then the endpoint uses it.
Yep. When generating a relevant memory request, it sets the TH bit, includes the PH, and the appropriate ST from its table, maybe in the header or prefix.
Wow. So TPH is definitely a system-level optimization.
Yeah.
Needs device, driver, firmware, and RC all working together.
Absolutely. And like LN and prefixes, TPH is also integrated into PCIe 6.0's flip mode. TPH info, PH and ST, gets carried in orthogonal header content type B OHCB.
So TPH, flagged by TH bit, lets endpoints hint memory handling for performance, especially in complex systems. Uses PH and system-specific STs for guidance. Needs system-wide support integrated into OHCB and PCIe 6.0. Okay, let's switch to extended tags. We mentioned the 8-bit tag. Why need more?
Right, the 8-bit tag manages non-posted transactions, matching requests to completions, 256 possible tags, often limited to 32 in practice.
Okay.
As PCIe speeds jumped up Gen 3, Gen 4, that became a bottleneck.
Not enough tags to keep the faster pipe full.
Yeah.
Especially with longer round-trip time.
Exactly. High bandwidth, potentially higher latency in deep systems. You need more transactions in flight simultaneously to saturate the link. 256 or just 32 wasn't cutting it for high-performance devices.
So more tags allow more outstanding requests.
Precisely. Moving to 10-bit tags allowed up to 24 outstanding non-posted requests, mainly memory reads, gives much more headroom to utilize bandwidth.
How do they enable this? Just make the field bigger.
Not quite that simple. Introduced via an ECN, formalized around PCIe 4.0, requires capability, advertisement requester, and completer both say, I support extended tags.
Okay.
And then enablement, an extended tag field enable bit in device control 2, usually set by firmware or OS. Needs system-level checks, RC support. Switches generally just forward them.
So hardware support plus software enablement. Now, how do 10 bits fit in an 8-bit field space?
This is where it gets a bit tricky, potentially implementation dependent. The original 8-bit tag field in DW1 still holds the lower 8 bits.
Okay.
The extra 2 bits, T8 and T9, get incorporated when 10-bit is enabled. Their exact location isn't fixed everywhere, might depend on PCIe version, TLP type, IP core design.
Example.
Some docs suggest T9 might be in a previously reserved bit in DW0, T8 may be combined with a control bit elsewhere. They might sort of overlay existing bits whose meaning changes based on context.
So parsing the header accurately requires knowing if 10-bit tags are active.
Yes, it adds that complexity. But the payoff is enabling higher throughput on fast links, crucial for things like NVMe SSDs, fast NICs.
More outstanding requests hide latency better, and the trend continued. 14-bit tags in PCIe 6.0 flip mode.
Yep, 16,384 possible tags shows the ongoing need.
So 10-bit tags extend the 8-bit field to allow a 1024 outstanding non-posted requests, vital for Gen 4 plus speeds. Needs hardware support, software enable. Extra bits integrated, adds parsing complexity. Expanded further in 6.0. Okay, final topic. Vendor-defined messages, VDMs, custom communication.
That's the core idea, a standardized framework for vendors or standards bodies to implement proprietary or specialized messaging.
For things not covered by standard TLPs. Platform management, diagnostics, firmware update.
Exactly. Device-specific config, custom control, extensible messaging using the PCIe transport.
How do they travel? Special TLP type.
They actually use the standard message TLP types, MSG, no data, or MSGD with data. Both use a 4DW header. Specific fields identify them as VDMs. Type field indicates message. Specific message codes in DW1 byte 7 are reserved for VDMs, like 0111NB, 011111B. Requester ID is in DW1.
And how do you know which vendor's message it is?
Crucially, the vendor ID is usually included either in DW2, DW3 of the header, if not used for address routing, or in the payload of a MSGD, like the DMTF vendor ID for MCTC.
Right, and payload for MSGD carries the vendor-specific data. The link field says how much.
Correct. If address routing is used, based on type field routing bits, DW2, DW3 hold the address. Otherwise, they might hold the vendor ID or be reserved.
So builds on message TLPs, uses reserved codes and vendor IDs. How are they routed? You mentioned flexibility for messages.
Yes, VDMs inherit that flexibility via the 3-bit routing subfield in the type field, much more varied than memory I/O config routing.
On options.
Route implicitly to root complex for discovery. Route by address, less common for VDMs. Route by ID, owner to endpoint. Broadcast from RC discovery. Local link only. Gather route to RC event reporting. Lots of choices.
Allows targeting specific devices, the host, or everyone. Very versatile. And MCTP uses this.
Yes, Management Component Transport Protocol. It's a standard for communication between management components like BMCs, power supplies.
Okay.
MCTP has a PCIe VDM binding. It encapsulates MCTP packets inside Type 1 VDMs, message code 011111B, uses the DMTF vendor ID, and leverages VDM routing like route to RC, route by ID, broadcast for discovery and communication.
So VDMs enable layering other standard protocols like MCTP onto PCIe. Very powerful. What's needed to implement VDMs? Easy.
Not usually trivial. Typically requires dedicated hardware logic in the device, like a BMC or endpoint logic, and specialized drivers or management software on the host side to generate process them.
So not just a standard driver thing. Throughput might be limited compared to normal traffic. Need VDM level flow control.
Potentially, yes. It's more for control, management, specialized tasks than bulk data.
So VDMs, standardized PCIe mechanism for custom messaging via MSG, MSGD, TLPs. Use specific codes, vendor IDs, flexible routing, essential for other protocols, MCTP, and vendor features. Often needs dedicated hardware software. Phew. We have certainly covered a lot of ground on TLPs today.
We have indeed. It's really foundational stuff. The PCIe TLP is incredibly adaptable, underpinning all that high-speed communication inside our machines.
Yeah, from the basic header FMD type, all those fields to the optional payload prefixes.
And then all those advanced features. LN for coherency, though maybe less used now.
TPH and steering tags for performance tuning.
Extended tags, absolutely crucial for bandwidth.
And VDMs for that custom communication. It's amazing how much is packed in.
It really is. It shows that constant balance in PCIe design efficiency and speed versus flexibility and extensibility.
And looking ahead, we see that big shift with PCI 6.0 flip mode, driven by needing forward error correction at those crazy speeds.
Right. Flip mode changes quite a bit. New header format, OHC replacing prefixes for a lot of things.
Mandatory 14-bit tags.
Explicit segment info, deprecation of some older bits like LN. It's a significant evolution in packaging and sending the data.
But the core concepts, TLPs carrying requests, data, completions, that still holds true, right?
Fundamentally, yes. Understanding the TLP structure we talked about today really gives you the groundwork for grasping these newer changes in flip mode. It builds on those principles.
So the evolution continues, meeting performance demands, trying to keep some compatibility?
Absolutely. It's a story of constant innovation responding to the need for more bandwidth, more efficiency.
Okay, so here's a final thought for you, the listener, to chew on. Considering this shift to flip mode, the ever-increasing complexity, what future innovations do you think will be necessary? What comes next to keep pace with these insatiable demands for bandwidth and efficiency in our digital systems?
Definitely something to think about. We encourage you to keep exploring PCI specs and related tech. It's a fascinating area.
It really is. Thanks for joining us for this deep dive.